Hello and welcome to my talk about the assisted planning and the setup of collaborative robot applications in modular production systems. My name is Wojtynek and I'm from the CoR-Lab at the University in Bielefeld, which is located in Germany. This presentation is for the ETFA 2020. Installing a robot in an industrial application, especially a collaborative robot, is a very challenging task because space in a robotic work cell is very precious and the task flexibility which is demanded is usually very high. The robot operator and the robot integrator are usually confronted with questions: where I'm going to place the robot in my workspace initially, where to place the peripheral components around the robot, and once the robot and the components are placed, can my robot reach, grasp and manipulate these objects around a specific working point? A solution to address the flexibility is the concept of modularity. For instance, by a modular production system. The modular production system contains a composable workspace where components can be freely arranged and rearranged according to a specific task. Components, for instance, like storages, carriers, and inspection components can be placed there. A user control panel gives instructions to the operator about the current task, and an embedded simulation simulates the robot movement before the real execution on the robot. In our previous work, we have published more details about the modular production system, which you can find in these references. Plug and produce is a key concept for the modular production system. The component is plugged in, parameterized with task-specific values, and it is ready for the production. Each component is built on a unified hardware platform, containing a mounting plate, a unified connector for power, network, and for an identification module to register the component to the modular production system. A self-description contains robot-specific data, like a CID model for collision avoidance and working points for grasping objects. Calibration points are used for an exact localization of the component in the real world, and the position can be taken over to the simulation model to perform an exact path planning with collision avoidance. Modularity and composability increases the production flexibility. However, the integration of components remains still challenging. Therefore, we like to introduce our approach of the interactive workspace assistant. This tool assists the operator during the workspace layout process, and it is meant to be a plugin for 3D simulation. The workspace assistant provides useful information for the operator in a dialog window. An internal scoring expresses the layout performance in one single value. For easier interpretation of the score, the value is color-coded before presented to the operator. The interactive workspace assistant is subdivided in 4 stages. In the input stage, the initial values for the process are defined. Later, in the simulation stage, the components are automatically placed in the workspace, in the composable workspace, and the reachability analysis is performed. The process moves on to the evaluation stage, where an automated scoring is presented as well as the generated layout to the operator. The operator decides now if he is satisfied with the generated layout or he likes to do some revision, which is performed automatically by the system or manual by him or herself. This iterative process is repeated until the operator decides to move on to the operation stage, where the generated layout is transferred to the real world and the assembly can be executed. Now let's take a closer look on the simulation model. The simulation model is expressed in the BPMN notation, which is used to describe workflows. Here we can combine the technical model with the user model. We can see that user activities are combined with some automated activities performed by the system. In our systems, we are using BPMN to describe workflows as well to program the robot. Here in the simulation model, we have expressed the input stage, simulation, evaluation, of course, the operation stage. So let's dive into the system. We start with the interactive workspace assistant. We are loading the CID model, and then the user has a parallel specification where he has to define the robot which he likes to use, for instance, a UR5 robot or another collaborative robot like the KUKA IVA. Then, as already mentioned, the problem where the robot is going to be placed. he can drag and drop the robot around here and place it to some different place. After all is specified, you can move on to the simulation stage, and the user decides if he likes to generate the layout for the task automatically with all the components, or he likes to do it manually. Or in a third case, if he likes to fine-tune or adjust some components. This is when he comes back from when he takes the decision to revise an existing layout. Here in the automated generation of the layout, we have a material flow strategy which was previously defined in the first stage, for instance a linear one, or we can also do a meander one. It depends on the piece flow inside the work cell. Once the decision is taken, a workspace analysis is performed in the simulation stage by the system, testing the reachability of each point or each working point at each component, and of course the manipulability in these points. Of course, it is very important to do a path planning. The workspace is very limited, so the robot has to consider the CAD models or the collision models of all components, and is performing a path planning. Once a successful path planning is there, the path is also stored. The layout algorithm for automated layouting is also described in detail in our presentation, in our publication. So when this is defined, we can go on to the evaluation stage, where the score and the layout is presented and the operator can take the decision. And usually I would like to see that the users are going this way to improve or optimize the layout, maybe to revise some components. Then we are going to a simulation stage, or maybe you like to revise some initial inputs like the position of the robot. Then we can go back to the input stage. But if you go to the input stage, we have to regenerate the layout or revise the layout, and then we can perform the automated score again, and we are again at this point. We are doing this iterative search as long as or until the operator is satisfied, and then we can store the layout and move on to the operation stage. In the operation stage, the position is roughly indicated by the simulation where the components have to be placed, but we need the exact position for the collision-free path planning, and we are inserting a measuring tool to the robot, and we can take over the exact position in the real world to the simulation model. Based on the simulation model, we can do a code generation, automatic code generation, and a platform specific, so for the KUKA IVA or for the UR5, or we can, in the online mode, we can stream trajectories depending on which we are preferring. And once all this is defined, of course, the production can start and can be also repeated. Yeah, and that's the end of the KUKA. That's the end of the interactive workspace assistant. On this slide, we can see some results of the interactive workspace assistant, and the formula represents the backend or the simulation backend for building the score, and it consists of 3 partial fractions to build the arithmetic mean. And the first fraction is the footprint, so the total number of components or the area below this component divided by the total area of the workspace. The second fraction is the reachability ratio, which consists of the reach components divided by the total number of components. And last but not least, we have the manipulability ratio. It is built by the manipulability index of each component in the working point divided by the number of frames. So we have defined some frames, for instance, at each component. There are like 4 till 6 frames defined at a certain edge, which the robot is trying to reach. And if it's possible to reach it, the manipulability index is calculated and used for this formula. Yeah, and during an initial initial study of this system, we had 3 objectives to see the performance of the interactive workspace assistant, and the first was to with objects with the same size and the same shape, which are just placed with the easiest strategy you can imagine. It's the linear one, so the linear material flow strategy. So we are placing each component next to each other, then we move to the next row and we're placing it again. And you can see if there's a collision or if there's some obstacle, it is shifted partially, so we can avoid some obstacles. The same would happen here with the socket of the robot. Okay, in the second objective, we generated with a randomized function various objects with various heights, shapes, and we tried to place it greedy around the sweet spot here with the highest manipulability, or let's say in the 3D dimensional space, it's somewhere here. And we are placing the components around like this. And in the third objective, we have used some real-world objects, the storages. We have this in the lab. And it has something like 4 lanes for the objects, and 4 lanes means 4 working points, and the components were also placed here, and we try to grasp at each point. Yeah, and depending on the reached or on the footprint and the other partial fractions, we get the score, which is raising from the simplest case to the highest case, which is later color coded for the user, and that because the user doesn't know what means 50% or something like that. What you can see here now is a small excerpt of a pilot user study. So here's a real user working, but at the moment this is the automated simulation stage, and the robot is performing the reachability analysis. So the robot moves towards various frames of each components, which are encoded inside the component, and if a frame is reachable, it's going to be marked green, and if it's not reachable, it's going to be marked red. And because of 2 components are fully not reachable, and here also the half of the frames are not are out of reach for the robot, the user gets here's the IVA assistant. He gets an advice, okay, here's something wrong with the reachability, and also he gets some advice, okay, try to move the block number 4 around a certain point to improve the reachability. And this is what the user is going to perform next. So he has the possibility to interact with the system and to revise or manipulate or improve the system by choosing a component and moving it around and improving the whole situation by his or her experience. So this is the last slide. It's about the conclusion, and we have presented the approach for the problem statement of the automatic workspace layout, which takes place in modular production systems. So modularity is a strong concept. However, it also introduces new problems to the robotic world, which has to be addressed and which has to be solved. So we have presented a workspace which is gradually composed and generated and optimized and revised by the operator, and also by the experience of the operator. So this was just a starting point. Of course, we can improve the usability. So instead of sliders, we can use touch input, for instance. And so we like to focus in future work more on the needs and the acceptance and the usability of the user to improve this intelligent or this interactive workspace assistant. Yeah, thank you for watching, and enjoy the ETFA 2020 online conference. Thank you.